Okay. Thank you so much for the introduction, Dr. Peng. It's a pleasure for me to be here with IEEE ComSoc, especially New York chapter. As you mentioned, I used to live in New Jersey for 7 years, and I really love city. Can't imagine a better place. You know, it's my personal opinion, but I really feel like New York City is like home for me always because I used to be there and around in New Jersey, was very close to New York City. So it's my pleasure to talk with you guys about futuristic direction that we're going to pursue in integration of terrestrial network and extreme environment. Let me a little introduce more Cleveland State University, which is a public research institution located in the city of Cleveland. We have approximately 17,000 diverse students, and CSU is very well known for its interdisciplinary programs and synergistic research programs, partners with several industrial corporations in the area and nationally. And so I would like to say CSU is one of the best public universities in Northeast Ohio. Just recently, under a plan called Jobs Ohio, CSU received a significant portion of $110 million state fund to prepare a pipeline for talents and providing more IT and tech related job, as well as healthcare related job in the state. As the other news, maybe you have heard Intel Corporation announced that they will open 2 new plants very soon in Ohio, which is relatively close to us. And this is around the $20 billion investments. And this announcement came with the promise of investment and research by more than $100 million. And CSU is part of the game. We're going to get a good portion of it, be partnering with Intel over the coming years on mostly manufacturing on chips and the related basically industries and technologies. So check it out if you are looking for faculty jobs. We are expanding. Make sure that you check our announcement. It's a good opportunity. It's a very fast growing institution. We'll be happy to have you there. And so that's about the place that I am now affiliated with. So I was introduced in the talk in the introduction initially. I'm an assistant professor at Cleveland State, and I'm in the middle of my tenure track by the way now. It's almost 3 years. I joined CSU, and the lab that I have and have good facilities over there is called Intelligent Communications and Autonomous System Laboratory. I have a couple openings there, and I want to use this opportunity to advertise it as well. If you are interested to join my group as a PhD student or postdoc, make sure that you check out my basically homepage. Dr. Peng, I'm sorry, I'm just, can you make me co-host because I want to see myself when I minimize the screen? Is it possible to
I think you are the co-host.
But okay, because if I want to minimize the video screen, not just the whole list of the participant, I cannot see myself. That's okay.
I can let me try and make you the host, so you have all the privileges.
And that might be better when I just see
Okay.
myself better.
So now you're the host. You're the host. Can you also make me the co-host? So just in case you're disconnected.
Sure. So okay. Okay, I'm trying to find that, but I cannot find this.
Oh, never mind. We can do that later.
Okay, sorry. So here's my research lab's information and the topics that I at the moment working on includes different intelligent communication solutions, and also basically new architectures for sensing and monitoring from extreme environments, particularly in underwater, which is my special interest over there. V2X and new technologies over there in order to connect vehicles in a more efficient way with the reliability and latency that we need in that industry is also another topic. And all the aspects related to smart cities is part of the research that I work on. So let's warm up with some basic graphs. Everyone probably in this room is familiar with important key capabilities and different usage scenarios of 5G, which was initially introduced by ITU like 5-6 years ago. If you might remember, it started with initially IMT Advanced Project that ended up into IMT 2020. So over there, we defined three main usage scenarios, including enhanced mobile broadband, which basically, as you know, it provides a high data rate for normal users to have 4K, and now I'm talking about higher 8K videos and so on. Then we have the ultra reliable low latency communication, which focuses more on the latency and mobility. And we have massive machine type communication, which basically the goal is here to have dense connectivity over a network, and IoTs are somehow fall in this category, which is a very basic thing that we start basically talking about 5-6 years ago. And the use cases and applications also are familiar to everyone, I believe. So through this graph, which I would like to mention a little bit more, is smart cities, which are supposed to provide dense connectivity with different applications and different examples within that applications. For example, in the recommendations and reports, we have the water management as one of those applications. Also monitoring and control of water quality and storage and distribution is basically one other application that we might be interested in. But that's not enough. As we move on into more connectivity around the world, and by more connectivity, we mean anytime connection, anything connection, including things to things, including things to human and human to human, and also any place connection, we might need to basically define more use cases. And that's also being predicted in ITU documents. I would like to give you an example of the Y series in supplement 56, which they define smart city categories under 4 categories: safer city, infrastructure, e-government, and city operation. And for each one of them, we see some examples being mentioned over there. But as you can imagine, still there are a lot of other places and examples we have not covered. So I'm trying to build the ground and make you prepared in order to see what exactly we are missing now. What is the shortage that we have that we are gonna basically put on the shoulders of new generation? And I want to talk with ITU's language, IMT 2030, and 6G, which now we are all talking about and preparing the wish list of what we want out of it. Many working groups are now start working on it. Some preliminary things are now out, but what exactly are we looking for? So we can talk about this for hours. And this is my list. It's not complete for sure. You can add to this list more items. But these are the things that I think they are relevant to what I would like to focus on in this talk and in my research. So in the previous generations, and talking about different capabilities of those 3 usage scenarios, we would like to increase these metrics and numbers. We don't want to go with higher speed. We want to go with lower latency. And we want to have more dense connection. So improving the previous capabilities is one thing that we would like to pursue, as well as new capability indicators, as I will explain when we get into our main conversation. Seamless and ubiquitous coverage. Definitely, coverage is now not completely all around the world and in different layers. Definitely, we need to increase the coverage to more applications, to more environment, especially more extreme environments, in my opinion. One thing that you may have heard a lot about this is 3D coverage. And 3D coverage basically means not only on the ground, but you may need to go and look into the space and try to connect that into the terrestrial network. Now, this is not new, basically, to be honest with you. And we have seen in 3GPP specifications, release 15 and 16, there are some good like link budget calculations and the basics of connecting satellites and HAPS into terrestrial network. And now in release 17 and very soon release 18, we'll see more coming about the specification of that connection. Also in the same information, we're talking about underwater. We're talking about connecting oceans and under oceans into this system. So 3D is not only goes up, but also goes below. And so the other half below the ground will also need to be covered with the system, which is the main focus of this talk around it. One thing that probably is missing in many of these, and I would like to emphasize on it, since we are going to put our devices and sensors and everything everywhere, definitely we will face some social and environmental impacts. And so I hope you're not influencing our planet in a negative way. Definitely that is a factor that will affect all our designs and all our futuristic, in my opinion, specifications from many different aspects and reasons, including energy, including pollution of environment, and so on. So that also is something we need to think more about it. Positioning is now another concern. And now, as you see in many terrestrial networks, they're getting into close high definition positioning and sometimes merging it with communication. There are a research track on that domain. That also need to be included in the next generation of basically systems and communication systems. And for sure, intelligence is something that we should add on top of the existing system. So said that, I would like to emphasize a little bit about underwater here and show you this nice figure, very cool figure of some biological and oceanographical surveys and monitoring, as you see, being captured. But is that the only application underwater? We look at it from only this perspective? Definitely not. It will impact our life more. And we will hear about this more as it's kind of tied with our life and jobs and many people's lives. So I want to give you some examples of underwater environment and how we interact with that. So for example, oceanographic data gathering is one of the basic things that you can imagine. Different type of sensors and different type of vehicles can interact and collect some data related to underwater. Pollution is something that is getting everywhere, including in the water. So monitoring that amount of pollution and maybe removing it would be a very immediate goal for the next 5 to 10 years. And I will talk about that in the next couple of slides a little bit later. As we are extending our wireless systems and different connectivity underwater, we are generating a lot of noise in different domains, different frequency bands. So monitoring that noise is also another issue need to be taken care of. There are a lot of disasters happening in the water, like tsunami or so on. So there should be some time-sensitive systems or seismic effect. Should be some time-sensitive systems that can monitor that and alarm people around the area, so we can make some good decisions. But as I mentioned, I have two main concerns for future in terms of environmental effects. One is the sea level rise, which because of the climate change we will see. And the second is the pollution, which basically is another problem. Pollution is something that we may not notice that much, but let me give you two pieces of news examples that you see. It is really serious. For example, in the left side, as you see, this poor whale died because of eating 100 kilograms of leader ball. Just one case that they reported. There are thousands and thousands more. And in the right news, you see the plastic bottle floating in the ocean, but they plastics are getting, converted into microplastics. So this is a research being done in the San Francisco Bay showing we have 7 trillion pieces of microplastics floating over there. We are just being there via storm water drains and so on. So this is really an issue. So there should be some systems to, help oceanographers and scientists to monitor this effect. And our role as communication engineers is very important here, in my opinion. So said that, let me put another slide about the ocean and the environmental issue, which is on this plan. I don't know if you have heard of this or not. This is a United Nations based plan, which is called Ocean Decades, and so calls for all these scientists for unlock the science for having a sustainable development oceans in 2030. It's not a national plan, it's an international plan. And there are 5 clear objectives mentioned in this worldwide plan, and I would like to go through them very fast. The first one is the goal is to have a healthy and resilient ocean. And so by this, I mean, we need an ecosystem, and a very natural ecosystem, marine ecosystem, which can be protected. The second objective is we need a predictive ocean in which, the society can have the benefits from the ocean. At the same time, the ocean's conditions are preserved. The third one, it should be safe. It should be protected from people. And the fourth one should be sustainably harvested ocean, ensuring that the food supply and everything are being available and provided. And it should be basically a transparent ocean in terms of data access. That's not being forgotten. We need to collect the data. We need all the information and the data being collected from different parts of the ocean for implementing more advanced technologies, again, in a closed loop to help better deal with the oceanic problem. So this worldwide plan is now being addressed from different perspectives and different communities. If you are interested to be part of this plan, I can connect you with the relevant scientists, as I'm part of, I also IEEE Oceanic Engineering Society, as well as ComSci. So over there, we have plans to connect different researchers into different groups. If you are interested, please reach out to me, and we will discuss how we can move on with this plan. Okay, so let me get back to the applications of underwater, as I mentioned. And I want to just, whatever I tell you, just make a comparison with the terrestrial. I can guess that many of you are very familiar with terrestrial, but maybe not that much with underwater. So it could be good mapping of just converting everything that I mentioned from underwater to terrestrial and vice versa. So one of the applications is real-time or near real-time water quality monitoring. So as you see, there is no that much real-time aspects here. That's a problem over there, which is already pretty solved in the air. We don't have that issue in terrestrial RF communication, but underwater, conveying the values that we collect from the bottom of the sea into the air is sometimes not real time. And so from latency perspective is lacking. The other issue is the bandwidth issue, because the bandwidth of communication, which I explain, and I don't want to exactly now say what type of communication, I will compare them, but mostly they are low bandwidths. So the possibility of sending high volume data such as multimedia and the video is very low. And the quality of the video drops. So that's also another thing, but definitely we are interested in multimedia, coastal and tactical surveillance applications. A lot of undersea and offshore exploration and oil pipe bridge inspection are going on now, very hot topic. Geological and biological processes need to be monitored. And finally, what I call Internet of Things underwater, which is now being around pretty for 5 to 10 years, almost, people in different groups working on this. And over there, the goal is to connect different static and mobile nodes, including sensors, including vehicles, human, and so on together. And that is a sort of IoT network being implemented underwater, although it's very heterogeneous and different type of sensory, different type of platforms, different type of data collection and data sharing, which makes the problem very difficult in terms of interoperability and interaction between different subnets of the system. So how can we connect with those nodes underwater? Well, if the nodes are static, definitely I would like to cable them, right? Cable connection is the most reliable one, although it's not maybe very cost effective, but it's most reliable. So we can tether the node. And also you can tether the vehicles. You can have the remotely operated vehicles underwater, very popular and very common type of vehicles underwater, although there are some issues, like they are severely limited in terms of maneuverability. And also, if you have multiple vehicles, they'll be getting tangled, as simple as this. So for those reasons, you may want to go in wireless, remotely operated or autonomous vehicles, which the first thing comes to mind, why not use radio frequencies? Well, radio frequency is absorbed in water, doesn't go more than a few meters. So if you have a vehicle, we want to connect it through radio frequencies. That vehicle need to resurface periodically to communicate via terrestrial node on the other side. How about visible light communication and optics? Well, that's a serious candidate, as mentioned also in many documents recently as a candidate for 6G and the next generation. However, there are some issues with that. So from one side, that can provide a very high data rate, I could say up to gigabit per second. From the other side, the environment underwater is not that prepared for that type of communication. Let me give you an example. So this is what we expect to see underwater. And pretty the same thing that you can see under very deep oceans. So if I want to play this video, and that's what the video from website I just collected for you to show you how clean and nice here is. And so even here, the color that goes through water, that was for scuba diving hand signals, but I meant that it's very clear in the water, and blue and green signal can go up to, let's say, 40, 50 meters maximum. Now, this is what I collected from the bottom of the river myself. And as you see, this is the reality. So murky water, and the light is getting easily scattered. And so the visibility low, it's not that much going, maybe less than 10 meters. So then optics might not look a good solution for rivers, for lakes, or for this type of underwater scenarios that we deal with them a lot in around ourselves. So the only thing is left is acoustics. Well, it might look very old. You're right. It's been around since like 50, 60 years ago, even more. But still, that's the only reliable technology and solutions that we have for distances more than 100 meters underwater. There is no other substitute for now for this technology. Although there are a lot of challenges in underwater acoustic communication. I'm going to go through them very fast and introduce them to you very briefly. So underwater acoustics is lacking in bandwidth. There is a limited available bandwidth we can use. The channel is impaired. Multipass is always there. Fading, smaller scale, large scale is always there. And so the propagation delay is much longer than what we have in radio frequencies. And also we have some other reasons for increasing the bit error rates, such as connectivity losses, which I call it shadow zone. And the reason for all those shadow zones is that because the acoustic signal, when it propagates in the water, it doesn't propagate uniformly, because the horizontal channel has longer multipass rather than the vertical channel. So sometimes you may hear that it might be more, it's funny, but it might be easier if you want to connect two nodes underwater. Sometimes it might be easier to send information from this node up to the surface using RF to the other side, and the other side from the surface down to the other node, because vertical channels show better better performance than the horizontal channel in terms of multipass. That also depends on the depths of water. The water, if it's shallow, if it's deep. So in shallow water, the reflections from surface and bottom is more serious. And then the question is, what is the shape of the bottom that can do the reflections? So the bathymetry of the bottoms also comes into picture. But for long distances and deep water, basically the effect that you see in this figure as being plotted by a ray tracing software is basically called laziness, which shows some bending effect of the ray over long distances. And also, as you see, because it bends and it's being affected by the layers of the water, it looks like a sort of waveguide that looks like that. And as you see, when it bends, there are some areas being left behind. So if your vehicle, if your receiver is in this area, you're lost. You can't receive any signal. And there is no way that you can solve it unless you come out of the shadow. So that's called shadow zone, and that's the effect of the acoustic wave underwater. However, for very short and distances, very close distances, that bending effect might not be that much an issue. Now, for each environment, the way that the acoustic wave propagates depends on many factors. It depends on the pressure or depth, depends on salinity, it depends on the temperature. And so in this figure is a typical sound profile that shows how the speed of sound changes with depth. So typically it's 1500 meters per second as sound goes at this speed, but as the depth goes up, the speed reduces, and then again it increases. So it's between 1450 up to 1550 for this typical graph that I showed here. For every environment, we need the sound profile of that environment in order to exactly be able to model how the sound propagates underwater. I'm telling all these to you because when we want to integrate this into our terrestrial system, we need to take care of all these things. So these all need to be taken care of. They are very important factors. So here is the graph that I would like to emphasize on this integration. Basically, we have that sort of IoT network that I showed you in the previous slide. On surface and on the shore, we can have the terrestrial network, and also in the space, we can have UAVs and also upper. Then we have different orbits of satellites, which are going to be our real non-terrestrial network being included definitely to the next generation. So as you see, there are multiple options of connectivity between the underwater to surface to the other non-terrestrial and to terrestrial network. However, because of all those things that I mentioned in the previous slide, there are some challenges. And we're going to investigate how we can solve these challenges. First of all, the spectrum in the underwater, as if you want to use acoustics for longer distances, which I'm talking about less than 40, 50 kilohertz, is not part of the spectrum that we use for terrestrial. So there is no coexistence at this time. There is no synchronization between these two portions as well. And also the connectivity cannot be continuous because the flow and the rate of data doesn't match between these two folds. Underwater, there are a lot of uncertainties, including in localizing the devices. The GPS denied environment, it's a very error-prone environment, so the localization of devices is an issue over there, plus other uncertainties from sensing up to communication, up to the other side of the link, end to end. So putting all these together, I'm calling for more investigation, whether how we can integrate this portion of the world into the existing terrestrial network with least minimum amount of effort. That's what we're going to do. So we need to be smart here. And that smartness is what exactly I want to talk about that today. So still, we are new to this topic, how to connect underwater to the air, but I'm going to put three options here, three solutions, very roughly, and talk about what I've done previously on these three domains. Most of them were part of my PhD efforts when I was at Rutgers University. And so at that time, we were talking about connecting the nodes within the water and from the water to surface. But now that this new generation calls for connecting a 3D coverage, now that all those topics are now being discussed again. So now that's the right time to again go back to our basic knowledge of basically what we can do underwater. So the first one is, I would like to basically call it, I'm avoiding to use this word, call it semantic communication, but I would like to talk about more content aware or behavior aware design. So that's not new in many contexts, I know, but in underwater is a little more complicated. And the nodes that we have underwater are usually, they don't have that much processing capabilities. And because of the energy issue and because of the implementation issue and cost. So what we can do, how much load we can put on top of them in order to be somehow aware of what they're doing. And also the network is being aware of somehow their behavior, can adapt accordingly towards futuristic semantic communication. So our final goal will be figuring out the intention and meaning behind the whole end-to-end process. We don't care that much about the communication itself when we are looking at the application. We want to send some data from the bottom of the sea into a cloud on the other side in a very remote distance. So my point is to get some meaningful data end to end. So I'm going to remove the redundancy. I'm going to remove what doesn't make any difference or doesn't have any information in other language, if I want to put it. So in this effort, I made some efforts on hybrid ARQ solution, which I call a correlation-based or correlation-aware hybrid ARQ, in order to transmit some data in the packet level. I tried to come up with some protocols that can consider the correlation among different sensors and also the similarity among them in a space and time. So spatially and temporally, we can calculate the amounts of correlation between them and use that information when it comes to the other side of the link for decoding. Just for your information, because the delay is very long, we may not be able to wait for the acknowledgement to come back. That's very costly for us. So we prefer to do as much as we can in the forward direction rather than closing the loop with the acknowledgement or NAC to resend the data again. So that was part of the thing I've done, baby step we took, but that's pretty good direction, as now we need to find more smart solutions for connecting underwater to the surface. The other thing is basically about how we can include the network and topology of the system. So in this work, which was part of a IEEE ComSoc student competition in 2019, which won the first prize in that competition, was basically how we can include the information in the network and use that in order to rebuild the network, in order to reorganize the topology. Assume that this is supposed to get some information about the litter and pollution underwater. So we have some vehicles, we have some static nodes, and they need to stay in a way that you can get the best informational value out of that regional zone. So initially we cast some local deployment, but over time we improve it and make it more efficient. That was also shown be a very efficient way, and I call it information-centric, basically ocean of things. It was appreciated by the community in 2019, and that's also in the same direction that I'm trying to convey. We need to be a little smart. We need to be a little aware of the sensing, and then use that jointly with the communication part. The third nugget is still missing. I need to have more computation on the other side. So the three nuggets of sensing, communication, and computing should come together in one package jointly. That would be the optimal and perfect solution for that. In the other part of the work that I've done, basically over there, we try to send video over very low quality, short distance acoustic links underwater. And over there, we crossed physical layer and application layer. So the reason that work is important underwater is if you go and try to look into different acoustic modems available in market, you cannot see that much flexibility. You can't see that much tuning in upper layers, mostly in physical layer and MAC layer. That's the maximum you can see. So going up to the full stack in the networking and also the application and crossing it back to physical layer is still a challenge underwater. So in this work, basically we use some scalable video coding encoder, which divides the video collected by the vehicle into the base layer and multiple enhancement layer. Those enhancement layer can be in time domain, can be in space domain, or can be in SNRM quality domain. And based on some metrics on the other side, such as the quality of service that we can define, or quality of experience that the user basically choose based on their application, based on their need, then we can tune and then choose the number of layers we are choosing. This cannot be implemented on the regular acoustic modems. It requires the software-defined modems. And so that software-defined concept is in research domain underwater is now popular, not in the real industry, which they are still using their traditional techniques for communication, which looks more reliable from other perspectives. So in this work, the goal was to capture videos from different angles. And then because of the overlap over there and then interaction between the nodes underwater, the system decides how to layerize the video and what type of information conveys to the other side of the network. And so basically it was some sort of understanding what they do, not only recording the video and just exactly streaming that. This is part of the video captured from the bottom of the river. And so you see different layers, different resolutions, and different frame per seconds. And so different quality levels are being compared here. And basically that was a first attempt we made to send a video. Of course, that doesn't work for long distances. That works only for short distances because of many acoustic bandwidth limitation issues that I explained. But that was a very good progress in that domain. These are the most popular commercial acoustic modems that I explained. And so these are the basic one, been around for years. And also this one is also a little more software defined, although all of them are lacking lot of issues and even adding more delays for processing rather than the regular propagation delay that we have in acoustic channels. So that also need to be calculated, the amounts of delay we have in the modems for processing. Now, that was the first direction that I would like to talk about, about being aware of what we are sending. The second thing is directionality in communication. Again, when you talk about radio frequencies, when you talk about millimeter wave, because you have very nice directivity over there, that might not sound very novel. But in underwater, think about very high wavelengths and very low frequencies of acoustic. The beamforming over there is really, really hard and not that efficient. Most of the hydrophones, which I call the equivalent of microphone and antennas use hydrophones, are very basically omnidirectional and sensitive to different levels of noise. There is a trend in underwater that they are working towards acoustic vector sensors. The one that I showed here doesn't have a good size. It's very bulky, but there are much more compact ones coming out in the market with a very high price. Now they are being used in many military applications, will be commercialized hopefully very soon. So the question is, especially in the receiver side, if you have some information about your sender, about transmitter, and you should be able to detect the direction of the wave, then you can distinguish them in space. So that's a sort of space division with the help of acoustic vector sensors being implemented for underwater. And it's a combination of different techniques. So here, what I propose here over there is trying to include that information, that space information, in the generation of the waveform. So over there also we use OFDM, but the way that you build your waveform can be affected by some knowledge of where the target is, and on the other side the same way. So that's the kind of joint design in waveform domain, and also including space in that, with the help of these acoustic vector sensors being used for this project. That sounds promising, although again, that's not that accurate for many reasons. And one reason is that you don't have the exact location of your target. You don't have it. So when you don't have it, you get easily sending your beam towards a wrong direction. And this cylinder that you see, I plot around this, shows something. It says that there are some uncertainties in the position of the vehicle, especially if the node is moving. That uncertainty gets larger and larger over time. It's like it's some dead reckoning technique that when you are on surface, you are synced. When you go down, as the vehicle stays more underwater, this amount of uncertainty increases. So maybe after an hour or 2 hours or so, you're getting like almost 50 to 100 meters of error, which is huge. So that cylinder after a few hours is very huge size. So then the solution would be, the third thing that I would like to talk about is about the uncertainty, and how can we deal with this position uncertainty? Can we somehow control it and manage it? Well, the other work that I little worked on it is basically defining some statistical interference area around the vehicle, and then assuming that while they are separated from each other, we can parallelly talk with them without an interference. However, as I said, because it's on a kind of probabilistic solution, it might happen that they get into each other, those regions. And so we may come up with some trade-offs of whether we are getting interference or we are missing the target by narrowing the beam and then just widening the beam. So that's a kind of trade-off between how we manage these beams towards some targets that we roughly know where they are, not exactly. So different type of positional uncertainties can be defined. One is internal, which is from the vehicles itself, and one is external, which is from the bystander outside. And these two are not always the same, but they can be converted. So in that work, we talked about that. So basically, we somehow were able to position the vehicles with a very, very inaccurate way. And that was another direction. A lot of experiments we have done in the past to collect the data and we do communication. Unfortunately, I don't have any underwater acoustic communication taking any recorded video from that. But what I can show you right now is the data collection with the a vehicle which can go on surface and can go down. Let's see why it stops working. So as you see, this is similar to what we're going to do for our future steps. We have something at the bottom, something on surface, and something on top. So the surface one, which I didn't talk that much about it in my architecture, has a critical role here in order to play the role of a smart gateway to connect these two media with each other. So that has a very critical role. A lot of conversation and discussion around that. How can it be? How can we distribute them? Is the kind of cellular system or cell-free system? They can move, they can be static. A lot of discussion around them is being going on. And so it's an open problem at this point. So just to basically summarize and just show some directions to future. The first thing that I would like to mention is that the key performance indicators are not always the same. So they should be matched, and the needs are not the same. As you saw, underwater is totally different environment. Still, software-defined solutions are not available commercially, they're not that much pervasive, and are very difficult to implement and tune. There is a good reason for that because of the cost and so on. One side, the other side is the adaptive and closed loop solutions, which you do every day in your RF transmissions. For you is something trivial. For underwater, closed loop and feedbacks are also a problem. So that adaptivity and reconfigurability that comes from software defined cannot be used in an efficient way. The other thing is that I believe acoustics and optics should be combined for different distances and different applications in terms of the data rate we want or the reliability we want. And so they need to be somehow covering each other in some sort of joint device. One thing that I would like to mention a lot about this is, unfortunately, we don't have a comprehensive standard in underwater. And that's the reason. There are a lot of reasons for that. I don't want to now go through that, but that's for sure is needed. For sure, we need to standardize all those things that I mentioned, which is not easy. So what we do now is basically either going with some basic models, or we collect the data, which is more appreciated. So for each environment, you see different data sets coming up. So we need different data sets be usable by other researchers and people so they can, try their system. And we can use that data set in order to more, getting towards the standardization. But still, we're far from a very comprehensive standard, although the efforts has been started. And just as an example, I can mention Janus standard from CMRE in the Center for Maritime and Experiments in Italy has been working on for a couple of years. Still, they're working on it, but still more work are needed in this domain. And as I mentioned, what we sense, what we communicate, and what we compute, they should all come together in one package. That's the key in order to make this whole end-to-end system happen from basically system perspective. Last but not least, intelligence. I didn't talk directly about intelligence, basically, but for sure, intelligence and machine learning solutions is something that need to be investigated. And that's another direction that many researchers are now pursuing. Okay, I guess I talked a lot, so I would be happy to take questions.
All right, great. First, thank you, Professor Mehdi Rahmati for this great talk. So now we are open to questions from the audience. Let me first. There's already one question from in the chat from Hashan. The question is how to integrate satellite network with the underwater network.
Well, that's a very good question. Basically, not integration in terms of the standard as now I talk, but previously and traditionally they are connected, because in many real oceanic data collection, you don't have access to the shore. So we are using satellite to convey the data back to our servers and our shore. So unofficially, oceanic data collection from surface is connected to the satellite, but the way I want to put it is a kind of pervasive way as we talk in the next generation. That also need to be studied. Still, the satellite itself as non-terrestrial networks option is being under study. As I mentioned, release 17 is now shows more details of it. Still, they're working on it. And we are waiting to see how that the other side goes. But underwater is a little more different medium. And so that is a little more problematic how we connect that to the other ecosystem that we already have in place.
Okay, thank you. There's another question in the chat. Guest one has a question about latency. So the question is, are we talking about latency from the object underwater to the surface? So is that the latency you mean?
Well, latency has different meanings. And so one is the propagation delay between the node, if I want to talk about communication perspective, which is very, killing the system, is a propagation delay. So think about the sound speed versus the light speed. When you're transferring underwater, you go with 1500 meters per second. And so when the distance goes up, it goes in the order of few seconds. Now think about a closed loop solution. You want to bring the acknowledgement back. Everything, the round trip time will be twice, which is for sure not a real-time system. That's one reason of latency. That's not the only one. We have a lot of processing lags in our nodes. So that will add up on top of the original time that we spent to transmit. But the main issue is the propagation delay between transmitter and receiver because of the acoustic wave.
Okay, there's another question from Professor Ye. So the question is, how do you do the underwater beamforming? Because in one of your work, you mentioned the beamforming, multiple transducers, and also another question from her is, if the sound speed is different, because if you're traveling at different depths from different paths, the speed could be different. In that situation, how do you estimate the which direction your signal is going towards?
Great question, Professor. Yeah, thank you so much. Great to see you here. So basically, the beamforming is being done in that work as a kind of analog beamforming, the regular beamforming as we do regularly by phase array. And so the direction that you want to, so the good thing about beamforming is if you know roughly where your target is, you basically tune your beam towards the target and you get rid of all those scattering and reflection, which kills our system. So that works well. There are a lot of restrictions. If you are close to surface, that might not work well. If you are close to bottom, that also might not work well. So it's a kind of middle range of the depths. That's the best, depths to implement that. And as I said, you have no exact location of the target. That was the reason when I showed that beamformer, I just showed it in front of a cylinder, which is large. So I'm just tuning the beam towards an area, not a specific point. It's not a laser point beamformer, it's an area, basically coverage. So very difficult. It doesn't go that well. The wavelength of acoustic wave is very large, so it doesn't get that much tuned in the direction that you want. So the accuracy of the angular accuracy is not that much. But again, when you do this, at least the amount of multipass, especially in the horizontal channels, which kills the system and generates a lot of fading issues, multipass fading issues, they're all gone. What remains for you is the large scale, and which is the factor of your attenuation, distance, and frequency, and spreading factor of the environment, which is pretty somehow deterministic, we can manage. So from that perspective, it was beneficial, but no way we can compare it with like the RF or millimeter wave beamforming.
I agree. Yeah, thank you. There's another very good question in the chat. So Michael asked this question. He says, shallow underwater transmission is an extreme multipass environment with SNR approaching 0 or even negative. So do some of the transponders use spectrum, which is able to decode in negative SNR? And Michael, actually, I see you, so you can unmute yourself and you can talk to the Professor Rahmati directly.
Well, Zhang, you actually, said it well. That's really what I wanted to ask. I've done a lot of work in ultrasound in acoustic environments like rooms, which is also another extreme multipath environment. But I don't see spectrum techniques often talked about in underwater, except in military papers regarding towed sonar arrays and stuff like that. So I just asked the question here. Thank you.
Sure. Thank you so much, Michael, for the great question. Basically, I have two works I didn't mention here. That was a joint work of myself, my former advisor, and the group in Italy on using spread spectrum and CDMA using chaotic codes. We use software-defined radio and their testbed, Loon, in Italy. And it worked great. The data rate is very low, but in terms of, as you mentioned, the SNRs combating the problem of that SNR issue, it works perfectly well. Unfortunately, the main goal in underwater is now to increasing the data rate, which CDMA is not a good option for that. So people are usually going for OFDM modems or so. The CDMA is the other option that we tried, not for the purpose of the data rate, but the purpose of the dealing with the SNR issue and with error rates. And that perfectly worked well.
Yeah, well, Shannon figured this out several decades ago, that if you transmit a negative SNR and you want to do so reliably, right, exactly, the data bait's got to be less than the bandwidth by the one plus SNR log, whatever. So yeah, that's the inherent trade-off, that if you want to live in a high multipath environment, you're stuck with low data rates. Of course, that's you want cameras and stuff that have high data rates. So you basically mitigate as much as you possibly can the multipath, but in shallow, that's really hard to do. So I'll be quiet and I'll let some of the other questions be answered. Thank you very much, John.
Thank you so much. Sure.
Yeah, thank you for this great question. Indeed, the shallow water, that's the most challenging environment for any communication method. Anyway, so let's look at the next question in the chat. The next question is also from Hashan. The question is, can IP support terrestrial and underwater communications, or it needs some enhancement?
So first of all, Hashan, good to see you here. Thank you for coming. So basically, what you mean here by IP means you want the network layer. Is that what you mean? The support of IP for some sort of networking?
Yes, yes.
Okay, so basically we have some research going on this to have full stack and higher layers and networking and up, but not in commercial part. So like Professor Tommaso Melodia's group in North System, they have some full stack software-defined testbeds, which they have the IP support. But again, that's something in research domain. It's doable, yes, to bring it back to the network. But in commercial models, that's something that still we haven't seen. So a lot of work needs to be done in that domain. Standardization is what I mentioned. I talked about that before with you. That something is not there. Janus is something starts to do work on it, but still a lot of work needs to be done on that domain as well.
Thank you.
Okay. Sorry guys, due to time limitation, we can only take one more, and after that we will have to conclude this event. So the next question is from Kit August. All right. Okay. So the question is, can you comment on the humanitarian applications for this solution of sensing? Are there particular signals or processed data types that can provide insights?
So generally, I can say there are a lot of applications related to humanitarian and I don't know, by humanitarian, you mean what exactly you mean? Means like social, like friendly or
Well,
environmental friendly?
You mentioned, yes, you mentioned earlier about the SDGs in the ocean. And so you probably have some idea in mind about some quick path to prove your theory about how this might be brought into that context and elevate people's awareness of how important it is, et cetera, to solve these problems.
Absolutely, absolutely. One of the goals of that ocean plan that I mentioned is bringing that to the awareness of people. And so the life of many people and fisheries and many other things are related to the oceans. So all the technologies that we are going to bring in should be in the same line, in the same way. And that awareness definitely is one of the main nuggets of that ocean decade plan. Also, as I mentioned, protecting the environment itself, protecting the people, and also like going towards more safer technologies we are going to put there to sense data. Like one example is biodegradable sensors that if being, eaten by fish or the other mammals, not again bringing back any illness or any disease back to the ecosystem. So a lot. I can name a lot, but probably oceanographics and biologists can bring more in their own field.
Thank you very much for describing these solutions.
Absolutely.
Okay, just one quick application. I am a big fan of scuba diving. When we do the scuba diving, right now you cannot do text messaging. Okay, say, okay, there's a shark behind you. You cannot do that right now. Or you cannot take a selfie and post them to Instagram. You cannot do any of that. So maybe with this technology, with what the things we're working on in the future, we'll be able to do that. So anyway, thank you everyone for coming. I really appreciate your help, and also I need to also thank all the participating chapters to bring this together, and thank you everybody. Okay, so that's it for today's event. We're gonna organize more events like this, but to help us improve, please fill up the survey, the post-event survey. Give us some feedback. So in the future, hopefully, we can do better. Also, if you missed the announcement at the beginning, so this presentation is being recorded. We'll send an email to all the registrants and share a link to the recorded video. Oh, by the way, Dr. Rahmati, can you put me as a host?
Sure, if you teach me how I can do that, I forgot. I'm trying to find it. So you want me to pause the recording or you want to do it?
Oh, yeah. That's because right now I cannot control that.
It will be stored on your site if I stop it.
I don't know. So put me back as the host first, and then let me stop it.
How can I do that?
Because I'm worried that if you you can write if you see the participants list.
Okay.
And then if you mouse over my name.
I got it.
There's a more.
I got it. Perfect. Make host.
Okay.
Really forgot how to deal with.
Okay. Yeah, I was worried that if you're the host and you stop the recording, then everything goes to your side. Okay.
Thank you so much for the invite.